teachers from outside of the city, and I will be talking about multiplication graphs in a little bit. Losing somebody. So why don't we just do a quick warm-up? So for the warm-up, first I would like to know how many of the multiplication rules do people remember? Divisibility rules. So what is a very simple divisibility rule?
All numbers are divisible by 9.
Okay. I gave up too easy of a divisibility rule. What about, let's say, 3? What's the divisibility rule of 3?
Some of the numbers.
Yeah?
Some of the numbers has to be above 3.
Some of the numbers are divided by 3. Do you know why that's true?
Yes.
Okay. Why is that true?
Well, you can write any number, like if you have a number with digits A, B, C, D, E, and so on. See, for example, I'll just give A, B, C. Then you can write the number A, B, C, D as 1000A plus 100B plus 10C plus D. And
Right, so your suggestion is that we have a number A, B, C, D.
Right.
Okay. So what should I do?
Works for any number, but A, B, C, D can be written as 1000A plus 10 plus 100B plus 10C plus which
Okay.
can be written as 999A plus A plus 99B plus B plus 9C plus D plus D.
Okay.
And when you take that in mod 3, you want that to be congruent to 0 in mod 3. So, since 999 is divisible by 3, all the stuff with the 9s goes out, and you just are left with A plus B
So
plus C.
clearly he has seen this many times. So let's go slightly back. So I completely agree, right? So you can take this apart, and this is a fairly simple taking apart. This is 1000A, 100B, 10C, and D. And I think this is actually fairly slick. So this is not something I would have seen immediately. To take this apart to 999A plus A, 99B plus B, 9C plus C, and D. So your suggestion was that if I were to group it this way, then I know that this is divisible by 3. Which means as long as the sum of the remaining digits is divisible by 3, then the number is divisible by 3.
Mm-hmm.
Okay?
And the same thing works for 9.
And the same thing works for 9, that's true. So why don't we try something else? So can someone give me a number, a 3-digit number?
Oh, anyone?
Anyone?
Okay.
Well, let's give someone else a chance.
216.
So 216. Okay? So let's just practice a little bit of the arithmetic. Let's say what happens when we multiply this number by 7, 11, and 13.
216. 7 times 11 times 13 is 1001.
That's true. So you're claiming that this answer is 216, 216. Can you give me? So this is obviously a nice result, right? So at least this is somewhat of a interesting result, right? So you multiply by this number, and you multiply by these 3 numbers. You multiply by 7, 11, and 13, and you get a number that seems to repeat itself. So does that always happen when I have a 3-digit number?
Yes. But only if it's a 3-digit number.
Only why is that true? Well, actually, so why don't we wait on that? So is everyone convinced that this is true? How does that work? Yeah. So why don't we roll back a little bit? Okay, so first, is everyone convinced that 7 times 11 times 13 is 1001?
Yes.
So can someone actually do it? So I can't do that multiplication in my head,
7
and I
times
doubt many
13
people
is
can.
91.
So why don't we actually just do it on paper? So a lot of the
7 times 13
a lot of the lessons today will involve multiplying, so why don't we just start getting involved in that?
Do you have a handle? Yeah,
We will. Yeah. So 7 times 11 times 13, are we all convinced that it's in fact 1001? Right. So if that is the case, then if we pick a 3-digit number, then it's not hard to see that if I multiply a 3-digit number by 1001, I might get, in this case, 216 times 1001, I will get 216, 216. So is there a way I can do it for a 2-digit number?
Yes, except that it would have to be, like, if the 2-digit number was AB, then when you multiply by 1001, you have AB, 0 AB, instead of just AB, AB.
Okay, so what if I want to get AB, AB?
Then you would multiply by 101.
Is that true?
Yes.
Okay. And what is the factors of 101?
It's prime.
Okay. So we are somewhat running away with this at the moment. So the question that I asked very briefly was, so let's say instead of the 3-digit number, right? So we use the example of 216, and I wanted a way to essentially go from 216 to 216, 216, right? And that just happens to be essentially here, I multiply by 1001. So let's say I have a 2-digit number, and I wanted to essentially form a similar pattern for a 2-digit number so that it repeats back to back. And the suggestion was that I multiply it by 101, which is a fair suggestion. And in this case, 101. So in this case, we know that this turns out to be 7 times 11 times 13. And in our case, this ends up being prime. So this is a nice pattern that we've looked at. And so why don't we transition a little bit to multiplication graphs, which is the actual topic that we'll discuss today. Hello? So right now, what I just handed out is a multiplication table, which I'm sure many of you have seen. So this is a multiplication table that lists basically all the products of numbers from 1 to 12 multiplied by all the numbers from 1 to 12. So looking at it briefly, I'm fairly sure there's no mistakes on the graph. Does anyone find any mistakes? Yeah, I'm fairly sure it's correct too, because I'm fairly sure it's done in Excel. So I didn't multiply it myself, so it's probably right. So now that we're convinced that this is correct, I would first like people to look for numbers on this graph that are multiples of 12. So can anyone give me an example of a number, or a pair of a number that generates a product that is a multiple of 12? Yeah.
11 and 12.
So 11 times 12. So let me go row and then column. So I'm going to say, if you say 11 and 12, I'm going to go over here. Right. So okay. So right now we are at the lower right-hand corner. Can someone else give me another example?
6 times 4.
6 times 4. Okay. You guys are finding all the hard examples. Does anyone have a number of very obvious examples? 12 times 1, yeah, that's 1. 12 times 2, right? 12 times 3. So I think it's pretty obvious that the last row and the last column are products that are multiples of 12. number. So why don't we circle on this table all the numbers that are multiples of 12. There are some pencils up here if you do not have a writing pencil. So I think everyone should fairly quickly at least circle everything on the last column and last row. And then, there was a suggestion earlier, actually there were multiple suggestions earlier, of numbers that are actually not in those two obvious columns, right? So, for example, one of the pair of numbers is 6 times 4. So there are a bunch of numbers that are in the multiplication graph. So there are a number of. You guys can get it. My turn? Sure. You're popular. I'm all selling you really fast. Must be good. So you should find that there are a number of other multiples of 12 within the table itself. So does anyone first notice something interesting about all the numbers that you circled, other than the fact that they're multiples of 12?
They seem to be forming like circle. Yeah, it's round shape that's spiral go around.
So there's something of a pattern in this table after you circle the multiples of 12, right? So in fact, and this is probably a good way to check, you know that if 6 times 4 is a multiple of 12, 4 times 6 is also a multiple of 12. So your graph has to be symmetric. It has to be symmetric across the main diagonal. So that's a good way, and after you're done, you should get a graph that basically has a row, the last row and the last column circled, and then something that looks like something of a star and a circle around it in the middle. Is everyone okay? So right now we are basically just looking at the multiplication table of numbers up to 12 multiplied by other numbers up to 12, and simply circling the numbers that produce multiples of 12. So now, this is a lot of numbers right now on this table. And I would like for some other way to visualize the things that are circled. So one way you can do it is in fact by using a graph. So let's say I write out the numbers from 1 to 11. Actually, let me in fact write out the numbers from 1 to 12. Okay? And I'm going to draw a line between every pair of numbers that gives me a product that is a multiple of 12. Okay, so we right now circled a whole bunch of these numbers already, so you can essentially just look up the row and look at the column and pick a pair of numbers that ends up giving me a product of a multiple of 12. So what is a really simple example in this graph? 1 times 12, right? So in fact, what happens to 12? What happens to number 12?
It's connected to everything.
So 12 ends up being connected to everything, right? So that makes for a very messy graph. So why don't I just take out 12 for a moment and look at this graph that is not as obvious. Okay, so now I'm looking at the numbers from 1 to 11, and I'm going to call this the multiplication graph for 12.
The 3 is paired with all multiples of 4, and the 6 is paired with the even numbers and the...
Well, okay, so why don't we slow down a little bit? So in someone give me one pair?
3 and 4.
So 3 and 4. Right, so this gives me 12. Can someone else give me another pair?
3 and 8.
3 and 8. Can I have another pair?
4 and 6.
4 and 6. 2 and 6.
6 and 10.
6 and 10.
6 and 8.
6 and 8. I think
9
we're
and
still
4.
missing 9 and 4.
9 and 8.
9 and 8.
6 and 6.
6 and 6.
Oh. Are you allowed to do
So,
that?
well, so let's talk about it in 1 second. Are there any other links that are left?
No.
Right, so we all agree that this is incorrect. This has all the links that are involved with multiplication graph of 12. Without the 12, right? So this is, and you'll see this throughout a lot of mathematics. We can sometimes, especially when we are defining these terms, so this is something that we are calling a multiplication graph, we can get away with defining some of the things we want to include or not include. So in this case, I thought 12 was too obvious, so I'm taking it out in this example. And whether this links exist or not is also something we can decide. Right? So why don't we just decide between the group whether we want to include these loops or not? So how many people would be in favor of leaving in the loops? Just getting back. How many people would be in favor of not having the loops? And many people are either asleep or waiting for the tape. So why don't we let's ignore the loops for now, and we why don't we ignore the loops for now, and we can talk about what some of the if we have time later, we can talk about what some of the loops are later. So right now we are ignoring, we're forcing all pairs to be distinct numbers. Okay? So right now this is the multiplication of graph of 12. So immediately there is something already interesting, right? So we already talked about one of the really interesting things is by including the number itself, you end up with a number that connects everything. And that's always true, so let's just take that out. And what else is interesting about this particular graph?
Every multiple, 7, 5, and 11 are not included.
So 5, 7, and 11 isn't connected
And
to,
1.
and 1 isn't connected to anything. Right? So why might that be the case?
Well, 5 and
Well,
7.
let's give someone else a chance. So why might that be the case?
Is it because they're prime? So 2 and 3 also prime.
Yes, 2 and 3 are also prime. So this is a
Oh, but 2 and 3 are divided with 12.
yes, 2 and 3 are also divided as 12. Yes, so we have a suggestion about whether all the prime numbers might have no links, and that turned out not to be true because we can see from this graph that 2 and 3 are connected to other numbers. So, and then the next suggestion was, I believe, whether they're relatively prime. Right? Was that your suggestion?
Yeah, to 6. And
To
to
6.
To 12.
Or
So
to 12. So what is the difference between a prime number? Yeah.
What's relatively prime mean?
Yeah, so does anyone know? So I will ask Sam to explain this.
Well, it means that the two numbers don't have any prime divisors in common.
Well, I thought it meant that you couldn't multiply the one number by any other number smaller than the other one and get a multiple of the bigger one.
No, I have just troublemaker. So I like Sam's definition, which is the cleanest definition. So relatively prime means that if you have
No, I was just trying to say.
I was just trying to say what the definition was of drawing your circles.
So,
Relatively prime means.
relatively prime basically means I have two numbers and they don't share any other factors, other prime factors. One is not prime, so one is never considered in that definition. So we do observe that 1, 5, 7, 11 are not connected to anything. And we also see that, in fact, 1, 5, 7, and 11 are relatively prime to 12. So can someone... Your
And
point?
5, 7, 11 are also prime. So
Yes, but
they can't
Is-
have any divisors in common.
that's
I'm
not
not saying
quite
prime,
true, though, right? So if I was generating a graph for 15,
5 would be
right?
connected to 3. And if
Yeah.
it was 49 and 7, it would be 3.
So even in this graph, right, we have two prime numbers that are connected to the other thing. Right? So everyone understands this graph so far? Okay. So right now it's still a mess. So why don't we make a determination that we are going to take out the nodes that are not connected to anything. So now we have this graph, and let's make another simplification, just for visualization purposes. So instead of actually having numbers on these, we'll just say they're nodes. One giant dot. So let's just make, this is what happens when I can't really draw. So let's just happen when they're giant points, and all the edges connect into the point. So can everyone on their own paper sort of draw out nice ways to represent this graph in which it's not nearly as messy as on the board. Some way to untangle the graph so that it looks much prettier.
Are we allowed to move them so that they don't intersect?
You can move the nodes such that they don't intersect. So basically you can move all the points any way you want. But if 2 points were originally connected, the graph that you generate afterwards still have to have those 2 points connected. Wow. We have a lot of very creative people in this room because I'm seeing a lot of very different designs from a lot of different people.
Well, if we set to make it cute. People have different ideas about cuteness.
So one of the things I thought about was doing something like this. This is going to get very confusing to me. So I thought about doing something like this. Right, but so that's just one way to represent it, right? I saw lots of interesting ways to represent it on many different pieces of paper. So basically, the only thing,
The numbers in the same place, so we are just actually moving everything around.
yeah. So basically, the only thing that I care about is that whatever points exist here still exist in the new graph, and then whatever connections they had existed between 2 points now still exist in this graph.
Oh.
Everything else is free to move. So it's just a way to basically make the graph look pretty to a certain extent. So now that we've done this, Sam is now handing out white paper. So clearly, one of the nice things to ask about is that, well, first, there's already a number of nice things to ask about here, right? So moving these points, and this is a somewhat advanced graph theory topic. There's a lot of constraints regarding how you can move these points and what shape you can potentially form by moving these points. But I want to look at something slightly different. So the problem that I would like to look at is, let's form multiplication graphs for other numbers. Right? I think it's a fairly natural extension. So, for example, what would the multiplication graph for, we mentioned earlier, I think we mentioned 10. So what would multiplication graph for 10 look like? So in that case, what you would do, right, is you would look at, so what would a multiplication graph for 10 look like? So first, from the audience, what numbers am I considering on a multiplication graph of 10?
2, 4, 6, 8, and 5.
So not even that, right? So what would the multiplication table for the multiplication graph for 10 look like?
It will look the same.
It will look the same, except that
It would be smaller.
it will be slightly smaller, right? So what will be missing?
10, 11, and 12.
It won't be missing 10, 11, 12. It will be missing
11, and 12.
11, 12, right? So you can still use this table to generate the other multiplication graphs, but it will either essentially be bigger or smaller, right? So why don't we work on the multiplication graph for a bunch of different numbers? So is everyone clear on what the multiplication graph is? So for multiplication graph of 10, we would use the numbers from what? What numbers would end up being used in this multiplication graph? 1 through 9, right? So basically, we use from 1 to n minus 1, and we draw all the connections between pairs of numbers that gives me a product that ends up being a multiple of that number. So in the case of multiplication graph of 10, I would draw all the edges that gives me the multiplication, that gives me a product that is a multiple of 10. Right, just like here is for 12.
Just define connecting to 2, 4, 6, 8.
Well, so let's wait on that. So why don't we actually split up the tasks? Because we have a lot of people here, we can cover a lot of multiplication graphs. So do you guys just mind counting off, I guess from, let's say 6? Yeah. 7?
23.
Let's count off consecutively. 8. I hate this rule, baby. 8.
9.
11.
Not 12. 13. Yeah.
Oh, 14. 16.
There was a 10 count.
Okay. 19.
19? What? 19 what?
You're making the multiplication graph for 19.
Oh, I was
So-
waiting for 10.
So it's
20, 21,
what number, so it's
22. 22. So I think Sam handed out. So I think Sam handed out white pieces of paper. So can you guys draw? So I want to see kind of two things. So first, the multiplication graph for the number that you assign in just let's say the circular ring where most of the numbers are there, and then draw a cleaned up version where basically you only see the nodes and sort of in the cleanest way you can draw it out. And then we'll take sort of all the multiplication graphs from like 6 to 22 on the walls, and we can look at what interesting patterns might evolve from all these graphs.
Oh, I think we should use this.
Yeah, you should use that.
For 19, I don't do
I don't
that.
want to take out my notebook.
For 10, I can do it right now.
Should we put our starting number?
Yeah. So can everyone also put in big letters the number that you're working on the piece of paper?
And then the next 8 points.
After 45 minutes of work, I completed mine. We realized
This number.
No.
40 times something.
Oh.
Sergey, you were 19, you're not finished yet?
I'm actually doing 10 as a bonus.
So three pretty graphs up.
Your number is 40. You can do
You're right.
That makes it messy. We also but we know that we don't know and then 9 times 4, 36.
We're missing quite a few graphs.
Pull the centimeter.
Whoa.
So we have 2 times 6 is 12.
Oh, you can make that does not include
2
11.
times 6 is 24.
The only numbers that are multiple to 11 are numbers that,
And then you
like 11 times something.
so these are
What would that graph look like?
That would just be 11. Just plain 11.
take this level.
Percentage is
Good job.
That's right. Those are very special. Those are very special kinds of things.
we will talk about
Things
it.
are nothing.
Whoa.
More important things, but will you use them?
And then high 4.
Times are slightly.
Slightly.
What are you doing? 21. Okay, for 21. You just write down the number. So look at the.
What was your number?
All the numbers for the
Your number was 95.
all the lines, 99, 30. All the numbers that are here write them out. And all the lines, they have to become the same number.
And you're also supposed to have room to do that kind of graph. The way you arrange it.
It's up to you.
Someone pulling
3,
out
Jim, are you playing?
I'm up there. I'm done.
What are you?
3.
I was 22. I had a grand Starburst time doing 22.
And equals 24.
Who was the size you equal to?
Oh, yeah, 8.
Who was the size 19?
Yeah, 19.
Who was the size 19?
Yeah.
This gave us a troublemakers. 19 is still pretty interesting, but you can also do 23.
If you would like, I'm doing 24.
Oh, okay. Okay, step 24. Can you do 25?
Sure.
Excellent. Okay.
So you can take any other number and
My troublemakers.
Anybody need more paper?
pick and take the number.
Who do I need to keep busy? You want to do 600?
No, thank you. I'm doing 19 and I don't, there's nothing.
That's okay. You can submit nothing.
No, it's empty.
Okay, can you just submit a paper with the number 19? Oh, we have? Okay. That's even better. So I'm just waiting for 24 and 25.
They're coming.
Coming.
21.
So, why don't we spend a little bit of time just looking at the graphs? So first, oh, thank you. Whoa.
19 is 12.
That is epic, 24.
All the different smaller numbers.
Wow. Yeah.
Maybe come up a little closer.
Yes, yes. Whoa, 21.
24, that's so funny. I know.
So why don't we?
That's exactly right, it's nothing. It's not.
So why don't we first? So why don't we spend like, let's say 5 minutes? Can everyone come up and just check to make sure that they think that all the graphs are correct, and see whether they think there's something missing. So just quickly looking at the graphs, I think there's some slackers in this class because there's a bunch of empty graphs. So
5 numbers, not slackers.
11 is missing something.
I know.
This one is missing, isn't it?
oh, someone else.
11 is missing a bunch of dots.
Oh, yeah, exactly.
Yeah, so or maybe the dots are so small you can't see them.
Yeah.
Wow, someone's actually correcting someone else's graph.
Wait, 16.
Oh, come on.
16 is the
We excluded points if you don't connect the traces. This was right, it's not.
we all have an 8.
Oh,
There's a whole bunch missing. 4 and 12.
Who was doing this?
Yes, that's sorry. Yeah.
so we have a number of corrections being made. There are some corrections that are suggested for 18 also.
That has to connect all the evens.
The right answer, but to a different problem. So we should notice that there was some logic to the whole thing after we saw it.
That's nice.
So can someone actually redo 18 in a pretty fashion? This will end up being a slightly messy graph.
Then 6, oh, I'm gonna go.
Wow.
Yep, yeah.
No, we're not.
That's how to prove that.
So we have some big slackers. Someone's working on 18.
Yes.
But we haven't proved it that way.
Okay, 18.
Wow, 20 points.
3.
I'm going to go get it divided.
6.
You're on alto.
Yeah, it is better.
So we have a number of revisions on the current graph.
It's an even cooler way of how
That's so neat. Do you have an extra copy of it?
Yes.
It's a great point. Of course, the whole thing is 7 patterns.
No, wait, no, not 3.
Wow.
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 Raise 12. Raise 12.
12 is the one we did.
Oh, so if you want to divide it,
During my project, a lot of these are
Yeah, someone's very
yeah. And they all connect to 11.
So we're waiting for 18 and then we can. Okay. That actually, can everyone sit back down for first?
See, this one is 35 to 30.
Yes. This one is really pretty though. I do like that one.
Is yours
Well, who's going to?
Okay, so let's, should we call it? Is it good?
Again, can everyone sit back down first? And now we have also revised 18 coming. So we have now a number of, we have covered basically every integer from 6 to 25 on the multiplication graph. So there are some very obvious patterns that come up immediately. So there's a few where somebody decided to throw nothing. So what are those numbers? So we have 23, we have 11, we have 17, 13, 19. So we have numbers like this, right? So is there something special about those numbers?
prime?
So these are all prime numbers. So one of the things that we can then perhaps generalize is perhaps none of the prime numbers have any nodes or anything on the multiplication graphs. So now we should think through whether this is an actual true statement, right? So we've observed a number of empirical cases. By that I mean, we did a bunch of examples. We saw that this could be true. And now we should somehow think about whether this must be true. So can someone suggest an idea about why primes might have no multiplication graphs?
Oh,
Can someone else suggest an idea? Yeah.
because when you're multiplying numbers that are smaller than that number, since prime, so the smallest number that divides a prime is itself, right?
Uh-huh.
So multiplying any number smaller than that prime, we cannot get anything that is the multiple of that prime.
Okay. So the suggestion is because so if this is the multiplication graph for n, and if n happens to be a prime number, let's say 17, then I know that in a time factorization, I basically get 1 times 17 or 1 times n. And that basically means that, and since the graph forms edges when a pair of numbers, the product of that pair of numbers ends up being a multiple of n. As long as this is a prime number, I can never have a multiple of n, or multiple of that prime number, without somehow involving the prime number itself in that product. Okay, so that does seem to explain why a prime number always has to end up generating an empty multiplication graph. So there are some other interesting patterns here, but let me pose a slightly different question. So let me pose a slightly different question, right? So this is an obvious pattern, a pattern of nothing. There also seems to be a number of patterns where you have one dot in the middle, and and you have basically a spoke of a wheel, or just radially, you have a lot of points that comes out from that central point, right? Well, this is not a pretty graph, but I think you guys get the picture, right? So I think we have a few examples of that up there. So let's try the reverse, right? So right now what we did was I gave you the number, right? And we can then draw the multiplication graph. So maybe it would also be interesting to figure out, given a particular graph, whether I could figure out the number that generated the graph. Maybe that's not possible, but let's figure out, for example, in the case of the dial, whether that's possible. So, well, first, so let's say that this graph has 60, so So let's say this keeps going, and it has 61 nodes.
Including the one in the middle?
Yes. So let's say it has 61 nodes, including the one in the middle. Okay, so that means 61 dots, right? So there's one dot in the middle.
I think it's less than 61.
And then there is 60 dots around the perimeter, where these represent some more than one dot.
Oh, that will work.
So is there a way to generate this graph? And is there a way to figure out what number generated this graph? Right, so
How, can you tell us why did you pick 61?
I think somebody else in the class will eventually tell us. So why don't we wait on that a little bit? So, first, clearly, one of the simplest ideas to do, and sometimes I do that, and it's not a particularly good idea, is to keep doing examples of this, right? I can do up to 1,000, 2,000, 3,000, eventually hoping that I eventually run across this graph. Right? That's clearly the exhaustive method, the method that actually works out pretty well, but it's not a particularly effective way in finding this in any short period of time. So maybe there's some other way in which we can figure out how this graph can arise. Yeah.
It's the multiplication graph of 62.
Oh, that's interesting. So there's a suggestion that this is the multiplication graph of 62.
Wait, no.
So I know why you might think that. So remember that we drop all the nodes.
No, I forgot to look at the. I thought that was even.
Yeah. So if I gave you a complete graph, right? If I did not drop off all the dots that are not connected to anything, this problem is fairly simple because I basically just add 1 to the number of dots, right? Because when I list it out, I just use the number from 1 to n minus 1, and I have all the dots. So I just add 1, and that would be the case. I don't think this is quite true, but maybe we can look at the examples that are already out there to see whether we even have something of a pattern that looks like that. So, apparently someone's already up here. What are the numbers that...
It's 2 times prime, but I don't know which prime.
So, what are the numbers in which we have a starfish-like pattern?
2 times prime.
Not yet. Well, what is it? So 2 times? Well, so let's use the numbers for now. So 10, 14, 22. Right, so the suggestion is, so because we have such a large number of examples, we quickly found a few examples on the graphs we've already generated where indeed we have the case of this starfish-like graph, right? So 10, 14, and 22, and someone suggested that maybe all numbers, all multiplication graphs of numbers in the form of 2 times prime will always give us something of this starfish example. So, is there a reason why somebody expected that? Why 2 times prime? Yeah.
Because there's the prime, the only multiple of that is the prime number.
Okay.
And
The only divisor of that?
yeah, only divisor of that is the prime number. So then you just list out all the multiples greater than that number of that prime number, and you get all the.
Interesting, right? So remember, this is not actually a very intuitive result off the bat, right? Because we remember that 1 times prime gave us nothing whatsoever. So the fact that 2 times prime gives us anything is already somewhat interesting, right? So now the suggestion is that let's just take the graph is already up there. So let's just take the example of 14, right? So I'm going to draw this in a much bigger fashion. this is the multiplication graph for 14. Multiplication graph for 22 looks like this.
The hand up.
Oh, yes.
It's the multiplication graph of 100.
Okay, give me 1 second. So right now we're doing the multiplication graph of 22, right?
How many does it have edges?
How many edges does this have?
Yeah.
So how many edges does this have? Can someone just quickly count it?
Dots, and it's the multiplication graph of 2.
So there's 10 edges here. How many edges are there here?
It's like how many?
So there are 6 here, right? So why? So first, there's something already interesting about these graphs, right? So there seems to be an odd number sitting in the middle, and what happens in the ring? And even numbers. And what about those numbers? So I have even numbers in lots of these graphs,
It's all even.
Yes.
right? All the even numbers less than n happens to show up, right? So that's a pretty interesting result, right, for 2p. Can someone suggest a reason why this might be the case?
Yeah, but that's
What?
even more. I guess the answer is no.
Oh, yeah.
Okay.
If you have like
Not
the center
using
being
this
P and you have a whole bunch of dots going around, like 2, 4, 6, 8, dot, 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 all the way up to 2p minus 2, then there are p minus 1 dots in total around the center. Like p minus 1 dots in the perimeter, and you add one more in for the center dot, and that's p. So that means the
Okay.
multiplication.
I understand what you're saying, but let me slow down a little bit. Okay. But let me look at, so right now we're saying that these are all numbers of the prime, of the form 2 times p. Right? So this is 2 times 11, and this is 2 times 7, right? So in fact, this odd number does show up in the middle. Right? So 11 is the number that's being shown, that's shown in the middle, and 7 is the number that's shown in the middle of these Starburst graphs. Right? So now, the interesting observation is, once this number shows up, I have a ring of numbers outside of it. So why might that be the case?
Because they're all multiples of 2.
And they're all multiples of 2, right? So specifically, because we're building a multiplication graph, so all these numbers, right, have to be, all these edges are formed between pairs of numbers that have to be multiples of the number itself, right? So all these pairs of numbers have to be a multiple, for example, in this case, of 14. So since it's in the form of 2p, right, the product of this pair of number has to include a factor of 2 and a factor that's p, right? And p itself has already shown up in the middle. So that means I still need a factor of 2 somehow, somewhere, which basically means any even number will give me my factor of 2. Now that's interesting. So this tells me that these edges definitely exist in my graph, right? But why is p in the middle? What happened to 2p?
Well, 2p is the number that is the multiplication graph of.
Yeah, right. So the reason why these are the only edges is because 2p exceeds the number on the multiplication graph. So we end up getting only these connections.
Because of our definition of multiplication graph.
Yeah, because of the definition that we sort of impose on the multiplication graph.
So what if you do 3p?
3p you'll get something like 21. You'll get instead of you'll have like
So
you could say like 2 of them. One is p, one is 2p.
the question came up about what happens in 3p, right? So we do have an example of that. Let's say 3 times 7, which give us 21. Right? So what does happen in the case of 3P? Well, actually, so can everyone, I know there's a graph up there right now, but can everyone sort of draw their own graph and test their intuition about what 3P might look like? So one thing we can see quickly is whether it's a starburst or not, right? Maybe it's still a starburst graph.
It's two Starbursts actually. Two Starbursts actually.
What did you do? Did you do the case of 21?
Yeah.
Oh, I see, but you drew the number 3 2
I
times.
know. You could just like connect them together. Put a 2P here, and then draw another
It's like,
Starburst.
like overlay them.
Yeah. Yeah, basically you do
Double
for 3,
flavor.
you have the factors of 7, and then do for 7, have the factors of 3, and then connect them and you say.
Okay, or you can like a real bicycle wheel where you got all the spokes coming out from one side and the other side.
Now 4P would get pretty interesting. 4P, when you get rid of 7. Yeah.
See, so right now you guys are doing small enough cases that you guys can just test it, right?
But wait, 4 is not prime, so
And
that would
plus,
be something.
You don't have to use
2
7.
squared times 7.
So if I were you, I would not use 7. I would pick a smaller prime.
3.
Right?
2 squared times 3. Wait, no, 3 times 3.
Or you use 5, right? So
Yeah.
the graphs go up here as opposed to picking a much
I
longer
did
case.
15 minutes.
Yeah, I see what you're talking about.
So I think it's pretty interesting to draw the case of 21. So it might be,
Even 15 is interesting.
yes. So 15 is also a similar case as 3P. But just drawing the case of 15 and 21 and just testing your intuition a little bit on what, on what you see. So very quickly, while people are still working, is it a starburst?
No, it's like a double Starburst.
So it's definitely not a pure starburst, right? So something else is also going on now that you include 3P.
It's actually, yeah, it is kind of like a bicycle wheel. Two things going on, the spokes going and intersecting. Yeah.
Didn't know.
Anybody brought their bicycle? Is at home? Oh, yeah. Why don't we go hijack one of the college students?
We're being filmed.
And you signed the form allowing.
So you're about to ask us about 5P next.
I'm going to ask for 200 people.
200 is not prime.
Wait,
199.
what about 3P? We haven't even. Oh, I see. Because why is also in respect to significance. That's why it's not the Starburst one center is from 2P, and the other center is 3. This center is 5 and 10. Without them, we have stuff that goes into everything will be visible by stream. That's what I thought was happening.
But then the thing is that 1P
So I'm going to cheat a little bit. And I'm going to look at the case of 15, which is also a case of free P. Right? So specifically, so we have some intuition before that P's and multiples of P's seem to matter quite a bit when I'm talking about multiples of P graphs. So in this case, this graph is a graph of 3 times 5. So the previous suggestion, right, was let's just look at what P is connected to. So in this case, 5 is connected to 3, 6, 9, and 12. Right? So why might that be the case?
Because they're multiples of 3.
Right? So a very similar logic to what happened in the case of 2P. Right? So I already have a factor of P that got picked up here. So I just need to somehow pick up the factor of 3, which means all products of 3 will get connected into my number 5. Okay, so I know that in my number 5 gets connected to 3, 6, 9, and 12. But in this case, I actually have other things also connected, right? So what else is also heavily connected? Yeah.
The 10 to the 12.
So the 10 is also heavily connected, right? So what's so surprising about 10? So 10 in this case is what?
Is 2P.
Is 2P, and or 2 times 5. So I guess this is slightly less confusing. 2 times 5. So, which means that it also itself has very similar properties, in the sense that it's also picking up a factor of P already. So, as long as it also somehow picks up factors of 3, it will also form products that will end up being multiples of 3P. So that means 10 will also be connected to what?
Multiples of 3.
So 10 will also end up being connected to multiples of 3. So you end up still with this Starburst-like effect, in which you have basically P and 2P connected to multiples of 3, right? So there was a suggestion earlier about it looking like a bicycle wheel, right? So essentially you have a number up here that's connected to a ring, right? And then a number down here that's also connected to the same ring.
And it doesn't work for 4P because then you would have to connect. You would have a Starburst for P.
Well, so let's hold on to 4P, right? So I'll leave 4P and 5P and 6P as sort of an exercise. Let's go back to the original question, which we have somehow diverted from, which I have accidentally erased. So we have a Starburst, right, which has 61 nodes, right? So now I'm trying to figure out which graph generated that, right? So let's go back to the case of 2P, right? So in the case here, we notice that there are 6 edges here, right? So how do I know that there are 6 edges here? I mean, one way is to count, but is there some other way I can figure out there are 6 edges here?
Half the number minus 1.
It's the number minus 1.
Half the number.
Half the number minus 1, but why is that the case?
It looks interesting.
That's true, it also looks that way. But why might that be the case? Why might I have 6 edges for the graph of 14?
6 to 7 minus 1.
Can someone else suggest an idea of why that might be the case?
You have 6 multiples of 2.
Yes, so I am basically, right, so this graph is connected to all the multiples of 2. And basically the question ends up being how many multiples of 2 there are less than 14. Right, so how many multiples are there? Right, so there are 6, right? So we good? So I think this is a fairly good justification of why there are 6 edges here. So the multiplication graph of 22, how many, well, I guess it's already written here, but does everyone understand why we will have 10 edges here? Does that make sense? So on the multiplication graph, for
51.
51. Let's say for 46, how many edges would people expect?
22.
So can someone explain to me why that may be the case?
That many multiples of 2 which are less than 46.
Right, so this is 2 times 23, right? So the graph, based on sort of what we've explored and what we understand, would involve basically 23 in the middle, right? And a bunch of nodes out that involves all the even numbers less than 46, so up to 44. Right, so I would expect, in this case, 22 edges. Right, so in my original case, and actually, while we're doing this, why don't we also look at the number of nodes, or number of dots, right? So, how many dots do we expect here?
7.
Why do we expect 7?
Because you have to add 1 to edges. Each edge contains, like if you were to exclude the middle dot, then each edge would have only 1 dot. And then you have to add back in the middle dot. So that becomes.
So the problem that you're mentioning is actually an interesting problem that is not so trivial. And there are many theorems in graph theory that relate these things. But let's just look at this specifically, right? How many dots are here specifically? 7, right? So how many dots are here?
11.
11. So one quick way to think about it, right, is
There
I
are
end
P
up.
dots.
I'm sorry?
There are P dots.
Yeah.
Yes. So one quick way to think about it is that I have basically the same logic as the edges. I have 6 even numbers on this graph, and then I add in my prime number and my odd number in this case. So here I would expect to have 23 dots.
But 61 is possible then.
No, because you would have
So I gave
61
61 as
dots.
the number of dots.
Oh, I thought it was the number of just those.
We were trying to find
So-
which multiplication graph has 61 dots, which is
So which multiplication graph
122.
that has 61 dots?
12 squared minus 22.
Why is that?
12 squared minus 22?
What?
Wow, that's a lot of math.
22. I think he was just using that as another way to express
That's
122.
actually true.
But
But why?
So, I think there is a faster way to do that than doing more math.
It's just 2 times
It's
Right.
2
times 61.
Okay? So,
Split.
and so in this case, I think we can pretty easily figure out that n is in fact 122. Okay? But just as an exercise, how many edges would you expect this graph to have?
60.
How many edges? 60, right? So that's pretty interesting, right? So we can now generalize this graph.
So 61, just if you have 61 dots without the middle, that's impossible, right?
So actually, so let me talk about that 1 second. So now we have a pretty interesting way to generalize, right? So we can now show for an arbitrary graph of starburst-like quality, as long as it has odd number of dots, right? What the multiplication graph, what n was that generated that multiplication graph. So the question came up with what happens if this number is even, right? So let's say I give you a graph with 60 dots. Is that possible?
No.
Can you tell me what n is? So of course a good way to do this is not to use such a big number. Let's use a much smaller number. Right, so
could this involve a 3p? Is what I'm thinking about, instead of 2p.
I don't know. So I will also leave that as an exercise for the moment, and we will move on. I'd like to leave things as exercises, especially things I haven't thought about a lot.
Do we know that the only starburst graphs are the ones of the type 2 times p?
I'm sorry?
Can there be starburst graphs other than graphs 2 times, for the numbers like 2 times p?
Not pure Starburst graphs. I mean, you can have like
So
bicycle wheels, but
that is also a pretty interesting question, and I think that's the question that Sam can address better than I can. But I believe there's a unique mapping on graphs and a number. So there's only one way to generate each type of graph.
let me guess, exercise?
Yes. I love exercises.
If you allow loops, otherwise 8 and 6 are the same.
So now, I'm going to talk about another different type of pattern that exists. Actually, there's quite a few patterns that exist here. But I'm going to talk about a specific type of pattern. So let's look at, well, I think 25 is really interesting. So I think 25 is really interesting because it seems like every dot is connected with every other dot. Is there another case in which that's true?
Like if you have a prime number squared, is there a multiplication graph for 9 anywhere?
So I see a multiplication graph of 9,
Right, everything.
right? So that also seems to have everything connected to everything else.
16 or 16. 16 up there, right above 9.
16 is...
No, because it's not a prime squared. It's not the
So-
prime.
That doesn't work.
The question that I'm going to ask specifically is, let's say I have 10 dots. That is not 10 dots. Right? So let's say this actually generates a complete graph.
You mean they're all connected to each
By that I mean all the dots are connected with every other dot.
100? No, wait, no, that's not. Yeah, I think it's the multiplication graph 100 something like.
So I'm going to stop drawing, but basically everything's connected to everything else. Right? And now I'm going to ask a very similar question to what I asked about earlier. So is there a way to figure out, for one, whether this graph is an actual multiplication graph, and two, if that's the case, whether I can figure out what number generated this multiplication graph? Right, so of course, since we have all these nice and beautiful pictures up here, a good way to start is look at the examples in which we do have something that resembles this pattern, right? So we have, I think, 25 here. 9 seems to be a fairly a trivial case in that we only have 2 dots, and the 2 dots just happen to be connected to each other. But so now we have these graphs. Is there something interesting about these graphs? Right, so actually, let me blow up 25. So there's something that jumps out at me immediately. Can someone comment on what they find particularly interesting based on the numbers, based on the nodes that are in fact even left in the multiplication graph after you take out all the nodes that are not used?
It's p minus 1.
Well, let's not, so right now, right, so I'm not sure what p you're referring to yet.
So each number is a square of a prime.
Okay, so these numbers do happen to look like the square of a prime, or so that's the suggestion so far. So
The number of points is p minus 1.
So number of points here happens to be 4. But before that, even before that, so is there something interesting about just the numbers that are being connected to each other? That corner of the room is somewhat quiet. I'm going to try to get somebody to answer this. So any observation about the numbers that are in that range? I'm sorry?
I didn't see if they all have the same factor of lines.
Yeah, so they all seem to be multiples of 5, right? In fact, they seem to be multiples of 5 up till 25. Right? So 5, 10, 15, 20. And in fact, all the numbers are connected to each other. Okay? Now, can someone give me some intuition about why these links might be connected to each other? Yes.
They're all multiples of 25. The products of any two numbers are all multiples of 25.
Okay, so the suggestion was, because 25 is equal to 5 squared, as long as I connect up two numbers that both have a factor of 5, I will end up with a number that will be a multiple of 25 in some way or another, right? So in this case, 5 is, of course, connected to 10, 15, and 20. That'll give me a bunch of products, right? 10 is connected to 5, 15, and 20. Okay, I think that's a pretty cogent argument. So if that's the case, right, shouldn't that work for 4 squared? Why square of a prime? Why not square of any number? Right, so, well, look into that for a second.
Because then it doesn't necessarily have to be a multiple of that number.
Okay, so actually, why don't we look at, so where's the graph of 16?
Right above 9. Right there, middle.
So 16, we can see, it's not a completely connected, it's not a completely connected graph. It's been post-modified. So it's not a completely connected graph, right? So clearly 16, just a prime square doesn't seem to work.
16 is not a prime square.
Oh, sorry. It's just any number squared is not going to work, right? So there's something unique about squaring a prime here, right? But yeah. But yeah. So there's something unique about the square of a prime here, right? So in fact, this is an interesting pattern that as long as I have two numbers that have p's in them, I can connect them up, and any pairs of these numbers will get me an edge. Does this work for square of all primes?
Yeah.
So let's say 49. What would you expect the graph for 49 to look like? And actually, can someone come up and draw the graph for 49?
Do you know how long that is?
Do you expect it to be very long?
Oh, actually, no.
Would you like to draw the graph? Want to draw it? Oh. Oh, no. They've been answering everything. You guys can't be off the hook completely. So. Oh. Yes. So can you break it? Oh, okay. Right. So you might expect, right, that this is a pretty cool graph, right?
Take out 49. Take out 49.
Yeah, take out 49. Oh, 49. So this is a pretty cool graph, right? N is equal to 24. And there are lots and lots of links going on in this graph. So you might expect that just as n gets bigger and bigger, the graphs will have tons and tons of connections, which we've already found out not to be true because all prime numbers, right? So 101, as we found earlier, the prime number 101 will give a graph of nothing. So 49 actually, surprisingly, at least surprisingly to me, isn't actually a graph with that many links relatively.
42 and 41. So just
Cool.
That's it?
Cool. Thank you very much. Right. So how many dots does this graph have?
6.
6. Right. So this has 4 dots, right? This has 6 dots. This is 7 squared, or 7 times 7.
Basically, if it's p squared, then it's p minus 1. Yes.
So there's a suggestion that if it's p squared, then it's p minus 1 dots. So why might that be the case?
It doesn't work for 9. 9
Nine's
only
not
has
prime.
1. Partially yes, it's two choice. Oh, that's right.
9's not prime. But
No, but
It's
3
3
squared.
9 is 3 squared. So
Oh, yeah, it works.
the reason it does work is you know that there are p minus. There are p minus 1 multiples of p that are less than p squared.
So the suggestion was, right, so we know from our early intuition from looking at the 5 graph and now looking at the 7 graph that because we're looking for products that are multiples of p squared, we need to somehow have one factor of p somewhere and one factor of p somewhere else. Because we know p squared itself cannot be found because p squared itself is not in our graph. Right, so that means any multiple of p will then now be connected to any other multiple of p. And any other case will not have both p's in the same product. So in this case, right, in the case for 25, that means any multiples of 5 will be connected to any other multiples of 5. So that means you end up looking for all the multiples of p that are smaller than p squared. Right? So how many are there? So how many multiples of p are there underneath p squared? That's usually p minus 1, right? So in this case, if 25 is equal to 5 squared, we end up finding that there are 4 numbers that are connected to all the other numbers. In this case, where we have 49, or 7 squared, we end up finding 6 numbers that are connected to all the other numbers. So, the earlier original question, and if you know the answer now, don't call it out. The earlier original question was that we have some number that generates a graph in which we have 10 dots, right? So, if you have an answer, can you write it down on your piece of paper and then show me? So now we're looking for the complete graph. So we're looking for a graph in which there are 10 numbers connected to all the other numbers on that graph. Do not yell out the answer if you know the answer. If you happen to know the answer, can you write it down on a piece of paper and then just hold it up and show me? Okay.
Oh. I can show you.
So we should figure out square, square, we can figure out the complete graph and minus 1.
So I see the right answer on many different pieces of paper now.
So what's p square?
So can someone now call out an answer?
121.
Right, so the answer
The previous answer is easy.
is indeed 121. Right? So 121 is 11 squared,
Yay.
and 11 squared ends up connecting 10 dots to 10 other dots. Yeah.
We discovered a curious little fact about multiplication graphs, and we're wondering if there's enough time to present it.
Sure. So clearly, there are two people who weren't paying attention to their own exploration. But they were now currently presented.
When did you discover that?
Like 5 minutes ago.
Oh,
So basically, what we were thinking is it possible to have any multiplication graph of this form where you have something like this. There are no lines across the middle. And this just goes on for a while. So in fact, there is no such possible graph. If you let n be the number that this is the multiplication graph of, and then you let this be a, b, c, and d, you know that n divides a times b, n divides b times c, n divides c times d, and did I skip something?
So far.
Yeah.
I'd like to see
And we want to prove does n, if we multiply all three of these, we get n cubed divides a squared b, sorry, ab squared c squared d. And from this, we know that n squared divides b squared c squared,
how do you know that?
because you're just squaring it. If n goes into b times c,
Oh, okay.
then n squared should go into b times c quantity squared. And so when you plug that in, you just get n divides 8 times d, meaning that there is a line here, but that goes against having no such line. So thus there's no possible way.
Very nice. So what does the graph of 8 look like? N equals 8. What does that graph look like?
Is that okay? I think it's right here.
Yeah, it's in the corner with the tiny.
Oh, is that the first one?
Is that a loop?
No, we're not allowing loops in that.
Sorry, is this a zone cycle? Or would N equals 9 then?
Yeah, it's the path.
Nine is or 9 is this case. So
9 is a cycle then?
No.
Just a single
Oh,
cycle.
sorry.
With possibly a loop on one end if you.
Yeah, sorry, I should have said would.
Yeah.
The only reason I'm worried is,
Ends at b45.
can I ask a question? The only reason I'm worried is because you assume there's 4 numbers, A, B, C, and D. Well, there's only 3.
Are you asking me?
In this,
It's possible to have 3 cycles.
yes, the graph has got 3 nodes and just 3 edges.
Yes. I mean, because if you have
That's why I was just focusing on 8, 9, my edges, but I just got it wrong, sorry.
2,
Well, anyway,
3.
so I think the session is now officially over. We can hang around and we can keep talking about graphs. But thanks for coming.